Hi, my name's Rhiannon Sanders, and I'll be narrating this presentation that's been produced by Lars Haneskog, the R&D Director of BioWorks. We at BioWorks are proposing a new concept for improving downstream chromatographic processes. We call the concept ECP, for Enhanced Capture Process. In this presentation, we'll give you just a quick overview of the basic principles. In particular, we'd like to show you some results that we get using our own resins in this approach. We've achieved significant improvements in purity and benefits for total process economy. As I say, this will be a brief overview, but there'll be links to more information and technical details at the end of the presentation. And you are, of course, welcome to contact Lars Haneskog if you have any questions. You'll also find his contact details at the end. BioWorks is a Swedish company from Uppsala. Our research, development and production facilities are all located at Uppsala Business Park. We're right in the heart of an area that's well known worldwide for chromatography and separation technology. A great advantage that we have is that many of our staff have in fact previously worked for pharmacy and GE Healthcare, and some of them each have 20 to 30 years experience in this business. For more than 10 years now, we've been developing and manufacturing Agarose-based resins for bioprocessing. Being located at one site with all functions, including production, allows us to be agile and respond fast to customer needs and challenges. Our resins are used in academic research laboratories and biotech and biopharmaceutical companies all over the world, from lab-scale purification to large-scale bioprocesses. The high-performance Agarose-based resins that we produce are called WorkBeads. WorkBeads are optimized to give the same results working in small scale as well as large bioprocess. This allows you to expect the same results whether you're using a small 1 milliliter column or packing your own 200 litre bioprocess columns. Based on a patented technology, these stronger beads have characteristics that generally allow faster separation with higher capacity. So I want to start by giving you an example of the ECP concept in the area where we've done the most work, purification of monoclonal antibodies. I'll then describe how this works for synthetic peptides and insulin purification. So bear with me if you're more interested in these two areas. We'll get to them in a bit. WorkBeads mAbs is the product that we've designed for improved monoclonal antibody capture. WorkBeads mAbs were developed by optimizing the base matrix, the alkali-stable protein A ligand, and the way in which they're combined. Now, protein A resins are expensive, and even if they are alkali-stable, any protein A resin will wear out due to bioburden and repeated cleaning in place. And most bioprocesses are developed according to similar strategies. So let's take a look at this. For a number of years, we've promoted the CEP strategy, corresponding to capture, enhance and polish, in that order, as you can see here. These three steps focus on first concentrating the target substance and removing harmful impurities, capture, then further removal of bulk impurities, enhance, and finally removal of remaining trace impurities and unwanted structural variants of the target, for example aggregates, the polish step. Now, using this approach, CEP, in a mAb purification process, the protein A resin, the sensitive, expensive resin, is positioned as the first purification step. I'll show you what I mean here. So here you can see three variants of mAb purification platforms, but all of them have the protein A resin in first position, the first blue-coloured box here. And many purification platforms for mAbs use expression in CHO cells. We've only, by the way, included chromatography steps in this diagram. It's very simplified, of course. The mAb is captured on the protein A resin, and that's followed by various techniques with decreasing specificity. As you can see, placement of the protein A resin in first position means that the crude feed from the CHO cells is applied straight onto the protein A column. And what's in this feed? Well, the feed contains some particularly problematic impurities. In addition to the IgGs, the mAbs that you want to have, there are all of these things that you can see here that are released from dying cells. Striving for ever higher antibody titers also results in increased amount of chromatin fragments. The large molecule complexes tend to absorb to various parts of the resin, and the feed also contains proteases that may break down the protein ligand. The consequence of all of this is a short lifetime for the protein A column, as well as lower purity and lower capacity. So we wanted to try to avoid applying all of this junk straight onto the protein A resin, and we set out to try to do this and reduce this problem. The solution is pretty simple. We moved one of the purification steps to prior to the protein A step. So instead of capture, enhance, polish, we now have enhance, capture, polish, and that's the basis of our proposed enhanced capture process. The aim of the first step is now to remove the bulk of the most harmful components from the feed. So you don't need any extra purification steps, just shifting the order and introducing a suitable resin for this purpose will solve a lot of the problem. So how exactly do we do this? Again, using mAb purification as an example, the step that we introduce is based on WorkBeads 40 TREN. You can see it here as the first blue box. This resin behaves as an anion exchange resin with balanced multimodal properties. The mAb passes through the first column without binding, but the harmful feed impurities are captured. So a CHO cell supernatant can be applied without pretreatment. And the supernatant can then be passed straight onto the protein A column, or you can use a holding tank. So the WorkBeads 40 TREN column is used in flow-through mode. The CHO cell supernatant is passed through the first column and straight onto the protein A column, which is the WorkBeads Affimab here. This can be done in a single process step or alternatively as two steps, as I say, using a holding tank. The WorkBeads 40 TREN column is then disconnected. It's eluted with salt and cleaned using sodium hydroxide. It's then ready for the next purification cycle. The protein A column is eluted separately. So what effects do we get using WorkBeads TREN in this way? The feed was passed through a WorkBeads 40 TREN column without any adjustment of the feed conditions, and 95% of the proteins and 99% of the DNA was removed without binding IgG, the mAb. Clearly, this significantly reduces the bioburden on the later protein A step, but it also gives improved purity after the protein A step. Again, if you want to see the data and examples of these, you can go in via the links at the end. So we've shown that introduction of WorkBeads 40 TREN as a first step in a mAb process can be very useful. Using the ECP strategy, endotoxins are removed over a wide range of conditions. You can use cation exchange, the WorkBeads 40S at the end of the process here, to polish off IgG aggregates and any trace host-style proteins. You reduce the bioburden on the protein A resin. You'll have an enhanced purity and yield of the eluted mAb. And of course, you extend the lifetime of the protein A resin. We've done a lot of testing of this platform. We've looked at, for example, the typical feed capacity of WorkBeads 40 TREN and whether the column size that you would need would actually be economical. And that all looks really good. But we're also testing the ECP concept to protect expensive high-performance resins in other platforms. So I want to quickly show you two other examples of how the ECP strategy could be applied. So another area where we've tested the concept might be interesting to those that work with purifying synthetic peptides, for example. You can apply a step to protect high-value silica RPC using WorkBeads 40S. Silica RPC columns are often used to purify peptides from the crude feed that's obtained after release from the solid phase. Some of the impurities stick to the silica resin, so cleaning in place will be needed. And even alkali-stable silica resins are damaged over time by sodium hydroxide cleaning. So instead, we introduced an Agarose-based cation exchanger, the WorkBeads 40S, as the first purification step. And the agarose resin is very alkali-stable. The WorkBeads 40S step has been included in a purification process for 10 kilograms of therapeutic peptide, and I can show you some of the data here. The WorkBeads 40S resin gave an extended reduction in harmful impurities, and at the same time there was a significantly improved purity of a synthetic peptide. So here we carried out a comparison between two cation exchange resins. The WorkBeads 40S in blue in the first graph and resin from another supplier in red. Note that 15% acetonitrile was used. The final purity when ion exchange was combined with RPC, on the right hand side here, was 99%. So combining an ion exchange step and an RPC step gave a powerful purification process. Collection of the target peptide was done to achieve a recovery of 92% for both ion exchange columns. And as you can see here, the WorkBeads 40S step itself gave a quite high capacity and purity, in this case a purity of 92%. Note also the rather high capacity compared to the other benchmark resin and the maintenance of high capacity at higher flow rate. This is, by the way, one example of the effects of the characteristics of the WorkBeads, which give higher capacity and often higher purity over a broad flow rate range. Note that with such relatively high purity already after the WorkBeads 40S step, you can do a lot of the peptide characterization work during development of the peptide with just this one-step purification. So this was a synthetic peptide. As you can see at the bottom, this approach in this customer example led to a threefold increased lifetime of the silica RPC column and reduced the production cost by 50%. But we've also looked at the effect of WorkBeads 40S resin in an insulin purification process. So here, stable Agarose-based resins can be used to protect the silica RPC columns, just the same way as the previous example. Again, our cation exchanger WorkBeads 40S was applied as the first purification step, in this case to protect two silica RPC columns in later steps. Note the substantial removal of the most hydrophilic impurities. So as in the synthetic peptide example, it can be shown that by applying a protective step, you not only decrease the need for cleaning and thereby increase the lifetime of the RPC columns, but a highly pure insulin can effectively be achieved in 3 steps. So these were a couple of quick examples on how to protect sensitive, high-resolution columns and at the same time achieve high final impurity. In conclusion, we can say that CEP is the general strategy, capture, enhance and polish, but ECP should always be considered for the sake of total process economy. The CEP strategy is generally a good starting point for purification process development, but it's sometimes unnecessarily expensive. The ECP strategy may allow protection of a less stable resin by applying a stable agarose resin upstream. Bioburden and reduced cleaning in place increase the lifetime of the sensitive column, and the shift in order can lead to a higher final purity. So we continue to look for improvements of existing purification platforms, as well as looking at the development of new generic platforms. So here are the links to technical data and more information. In these blog articles, you can find downloadable documents, white paper, application notes, things like that. So thank you very much for listening, and don't hesitate to get in touch if you have any questions.